Okay, I'm starting now. Hello, everyone. I'm Weixuan Zheng, and I'm an undergrad working under Professor Marc Snir's lab in the University of Illinois Urbana-Champaign. The topic of my presentation today is an implementation of the network backend of lightweight communication interface using UCP. First of all, I would like to give a brief introduction of the lightweight communication interface. So first, let me talk about the motivation of the project. Traditionally, the bulk synchronous programming model combined with MPI as a communication library has dominated the field of traditional HPC programming. However, this BSP model has its limitations. First of all, it introduces some unnecessary global synchronizations. In addition, high demand for balanced load across processes is needed to ensure the efficiency of computation. So the picture to the left is a schematic for BSP model. The task is split into different nodes and they go to synchronize and they continue to split. In order to deal with those limitations, asynchronous many-task runtime systems, or AMTS, can potentially solve the limitations. In this computation model, computation and communication are overlapping, and the scheduler can automatically determine the dependency of tasks and automatically load balance the different tasks. It also removes some unnecessary synchronization because it explains the dependencies of the tasks. So the picture on the right is a description of the AMTS, where each task have dependencies, and the task can be run if the dependencies are met. So this new AMTS leads to different communication characteristics. So usually more messages are exchanged, and due to the larger message size, larger message number, each message tends to get smaller, and the communication pattern is dynamic. And also, there are more point-to-point communications because of the explicit dependencies between tasks. It is also typically conducted in a multi-threaded environment. And these communication patterns are not unique for AMTS, but for other irregular applications, such as graph analytics, sparse linear algebra, and fast multiple method. Unfortunately, MPI as a communication library is not typically optimized for those cases. For example, MPI's multi-threaded performance is not ideal. So if MPI is used as a communication library to transfer data between the nodes, it will quickly become a bottleneck in the computation, and a better communication library is needed to deal with those challenges. So yeah, this is why the project of lightweight communication interface is proposed. It is designed to work better in the context of new communication characteristics. So what is LCI? It is essentially a low-level communication library with C API. Unlike MPI, the LCI is not intended to be exposed to programmers, but it is intended to be used for libraries and frameworks. Currently, we support three types of network backend. We support libIBverbs, which is InfiniBand, and libfabric, also known as OFI. Where the topic of our presentation today is UCX Backend, which is still in development. Currently, we have several clients and collaborators to our project, which include analytic frameworks like Gluta, dGalosis, and dLigra. We're also in collaboration with Parsec at HPX. So next, I will talk about the design principles for LCI. In order to fit the new communication characteristics better, the first priority of LCI is multi-threaded performance. To improve multi-threaded performance, we attempt to minimize the interference between different threads. We use fine-grained trilogs to minimize the interference. Also, we replace the centralized MPI metric queue with a hash table. However, we're putting more restrictions on wildcard send and receives. We also the second design principle is to provide a versatile communication interface. We provide various communication primitives. For example, we can support either one-sided or two-sided send receive. And send receive pair are for two-sided, put get pair are for one-sided communication. We also support various completion mechanisms, which include synchronizers, which works like an MPI request. We also support function handlers, which are like callback functions provided in UCP. We also support completion queue as a completion mechanism. The users can compile any communication primitive with almost any other completion mechanism so that they can find a combination that best fit their application. The third design principle is to give explicit control of communication behavior and resources. For example, user can have direct access to registered buffers, and the memory registration, deregistration function are also exposed to users. The communication protocol can be chosen explicitly, whether it's eager protocol or rendezvous protocol. And the progress function is also exposed to users so that they can decide how frequently they want to call the progress function, depending on the workload progress. So after that, we will talk about the communication protocols for LCI. The first one is the eager protocol. And this is primarily used for send and receive medium messages. So one thing to note is that we're replacing the MPI metric queue with a hash table here. The protocol mainly works as follows. First of all, inside the progress function, we're posting multiple receive requests to the network backend so that the network backend is always ready to receive some new messages from other nodes. And the network backend also provides information on completed operations to the progress function so that it can know how to handle these received messages. And once the progress function is notified of a receiving message, it inserts a relevant entry into the hash table. Whenever the user call LCI receive, it also inserts an entry into the hash table. And if there's a match of the entry between the hash table, the communication is officially complete and the notification is provided to the user-provided completion mechanism. If user calls send, the data is a user-provided buffer is first copied into an LCI packet, which is allocated by this packet pool. This copy ensures that the user buffer can be immediately reused after the send returns. And after that, a send request with the content inside LCI packet is posted to the network backend, which completes the send operation. So this is a rendezvous protocol we used for basically send long and receive long messages. The process is an exchange of ready to send and ready to receive messages. First of all, whenever the user calls send long, it sends a ready to send message to the receiving side, and the receiving side gets this completion notification through the progress thread, and it inserts an entry into its local hash table. And whenever the user calls receive long, it inserts another entry into the hash table, which results in a match. As a result, the progress thread is replying ready to receive message to the sender side. And the sender side, once gets this message, it initiates an RDMA operation that delivers the data to user-provided buffer, which completes the rendezvous protocol. So after talking about the protocols, we need to talk about the backend, like the functionalities required by them. So this is just an overview of what each component is doing in the communication process. So the LCI upper layer manages message matching, which is achieved by hash table. It also manages the packets, which basically deallocates the packets related to send and receive. It also manages the rendezvous protocol, and it also provides notification to user-provided completion mechanism. The backend communication layer needs to support three different types of messages. First is plain message passive without tag matching supports, so it is for send and receive pair. It should also support RDMA write. It's either with or without signal, which is used for our rendezvous protocol. It should also be able to provide completion notification to the progress function through completion queue polling. And our backend interface are designed initially with IBverbs functionality in mind. So most of the functions should be very similar to the ones provided in IBverbs. So this is a summary of our backend interface. So we first need the initialization and finalization functions, which should be required. Otherwise, we cannot do anything. And we also have a memory registration function, which are for RDMA operation. And we also have some posted communication functions. For example, two-sided functions, we have post send, post receive. And one-sided operation, we have post and put and put immediately. This put immediately is just for RDMA with signal. And we also need to have this post CQ function, which just gives notification to the progress function about completed operations. And here is a summary of how our backend interface map to IBverb functions. As I have already mentioned, the mapping is very straightforward. It's simply one function matches with exactly one in IBverbs. So this is a general scheme for our LCI functions. Inside the initialization function, the LCI upper layer registers a large memory buffer and breaks it into smaller buffers. So each of those smaller buffers is a packet. And we pre-post thousands of receives to the network backend so that it is prepared for any incoming send. Inside the progress agent or progress function, the LCI upper layer checks for completed receives by calling PostCQ function. And depending on different types of messages received, it acts accordingly. And it reports the receive request so that this node is always prepared to receive more incoming messages. So yeah, this is so now let's actually get into the actual UCX backend. The methods are still straightforward, but with some differences. The major difference is that currently UCP does not have a put with signal function, and it also does not provide a post completion queue function. So we need some workaround to that. The other methods are mostly straightforward, like send and receive are directly matched, and put are directly matched. So yeah, so this is our current solution to RDMA write with signal. Essentially, the main idea is to use a sequence of put, first, and send to make Mkey. So inside the callback function for UCP put ABX, we first call UCP worker first, and then call UCP text to the remote peer so that we can deliver some completion notification to the receiving side. The UCP worker first is there primarily for the purpose of ensuring that the completion of the UCP put at the remote side is before the UCP send, so that the completion notification is guaranteed to be after the remote completion. And this is our solution for Poole completion queue. First of all UCP communication operations are posted using UCP flag no immediate completion, except for UCP put ABX. The reason for this will be discussed in the next slides. Using this flag basically ensures that the operation is never completed immediately, and therefore its callback is guaranteed to be called after it completes. This is the structure of our completion queue. So each UCP worker or LCI SI endpoint has a completion queue associated with it. And each completion queue entry stores some information like operation type, protocol number, message size, etc. So these are required information by the progress thread so that it can handle different types of messages accordingly. Each CQ entry is created whenever we call this LCISD post function, which is the function that posts the communication to the network backends. And the CQ entries are pushed into CQ. The related UCP operation is completed, and it is pushed inside the function handler for those UCP operations. And the CQ entries are passed to upper layers, aka LCI progress, where it posts the completion queue and it provides information for completed operation. So yeah, this is an explanation of why we did not use the no immediate completion flag with UCP put. So currently there seems to be a bug with this flag. So the major thing is that if I use this flag with UCP put ABX, the callback function can be invoked, which means the local completion is fine, but the data is never delivered to the remote buffer. And we also tried calling UCP worker flush ABX or UCP EP flush ABX, but calling those functions does not help, and data is still not delivered to the remote buffer. And the current workaround is still simple. We first check the status of the operation. Basically, if this operation completes immediately, we explicitly evoke our callback function after the third. And inside this callback for UCP put, we do not push the CQ entry to the CQ. Instead, we push the entry inside the callback for the third, which is used to signal the remote side of the completion. And yeah, that is our current workaround for that. So in our implementation, we also notified an issue on the coarse-grained blocking log. So basically, UCP has a more coarse-grained locking issue than libIBWorks. So in IBWorks, the queue pairs, shared receive queues, completion queues have their own logs. So the posted third, posted receive, and post CQ do not interfere with each other. And typically, post third are performed in worker threads, and post receive and post CQ are performed in progress threads, which makes the communication efficient by minimizing the interference between threads. However, UCP uses a single lock to protect a UCP worker. So whenever we call UCP worker send or UCP worker receive or UCP worker progress, these functions will interfere with each other so that worker threads and progress threads are competing for the lock. And these locks are blocking lock. So it will cause a problem because progress threads can be blocked for a very long time by waiting for the lock, and therefore the progress function might not be called frequently enough to make enough progress on the communication routines. To solve this issue, we tried using a try-lock wrapping around all UCP functions, and we do this to allow the progress thread to obtain the log more often and call its progress function more often so that we can basically make the progress communications more often. There's also an issue of finalized receive. So during finalization, where posts were posted many receive requests, there can still be unmatched pre-posted receive requests. And however, UCP will throw a assertion error if there are any outmatched receives. And this is causing a problem because it doesn't allow us to finalize correctly. So currently the workaround is simply have an empty finalization function to circumvent this error. So possibly there are some better solutions. For example, we can keep track of all posted send and receive requests and cancel any of them during the finalization. Or for the UCP side, we might need a functionality that allows UCP to automatically cancel a matched receive during finalization. Or we might need a configuration option that disables this requirement in finalization. So yeah, we don't have this issue in libIBWorks. So this is a unique problem to the UCP backend for now. So let me summarize some of our results to test the performance of our UCX backend. So this is our experiment setup. We run our benchmarks on SDSA Express. So each compute node, it has two CPUs, each with 64 cores, and it has InfiniBand Connect. The libraries used are here. So we used OpenMPI 4.1.1 with UCX. We used LCI with IBWorks Backend. We also used LCI with UCX Backend, which is the one to our interest. And in the experiment, we used at most one thread per core, and we always have one dedicated progress thread in the case of multi-threaded environment. And the progress thread is simply a thread that is always calling our progress function and no other operations. And we run our tests on this multi-threaded ping-pong benchmark. In this benchmark, each thread sends a message to its peer, and after this message exchange, the role reversed, and node 2 actually sent data to node 1. So we're using a very small set window. It's only one send and receive pair per thread, and we used a large number of steps, which is 1,000. So we tested our latency for different backends. So first of all, we compared our latency versus thread number. So we used those number of threads. And the libraries compared are LCI with UCX, LCI with IBWorks, and MPI with UCX. And the results are summarized below. So yeah. So generally, we can notice that LCI with IBWorks usually outperforms LCI with UCX and MPI with UCX. So basically, in most situations, the latency for LCI IBWorks is lower, except at this point, the reason of which will be discussed next. So yeah, this one is also LCI IBWorks also performs a little bit better than the other two backends. The main reason we hypothesized is that IBWorks use a finer grid locks, and UCP progress, send and receive share the same lock so that they might interfere with each other in the multi-threaded case. So this is an explanation for, well, it's actually a hypothesis for this latency drop of LCI with IBWorks. So the threads are spread out in two different sockets because we have two different CPUs. However, we only have one progress thread, so half of the workers will go across the sockets, which introduce a high communication overhead. But we still need to experiment with NUMA ACTF and interleave flag so that we can explain why this latency drop does not happen with LCI UCX and MPI UCX. We also tested the latency versus message size. We noticed that as message size gets larger, performance gets similar. And this is likely because hardware bandwidth becomes a bottleneck, and software overhead contributes very little to our final latency. And from this plot, it can also be seen that LCI with IBWorks has a better performance than the two others. And LCI UCX is a little bit better than MPI, but these performances are similar to each other. So as I mentioned before, we have a desire to wrap a trilog around our UCP functions to try to solve this coarse-grained blocking log issue. So whenever the function is unable to obtain the log, we directly return with LCI error retry. So this hopefully might make the progress function to be called more often. And the plots below are the results. So we have, the results are kind of different for different message size. So for short messages, it degrades performance. It introduces a higher latency. For medium messages, it improves the performance. So it reduces the latency. For long messages, the performance are roughly the same. The two lines overlap with each other. The hypothesis is, it's mainly because of the progress function. So if the progress function is called more often, then for smaller messages, progress function has little task to do. So calling this more often is not useful at all. But rather it introduces more overhead. For medium-sized messages, progress function has more work to do, and calling this more often might be able to speed up the communication and progress. For longer messages, as discussed before, it's likely that the hardware becomes a bottleneck and software overhead has relatively little effect on overall latency. So there is still a lot of future work for us to do. First of all, the current implementation of this backend is far from complete, and there are a lot of places to optimize and a lot of issues to solve. For example, the issue with UCP put and the unfinalized receives. And regarding the testing of benchmarks, we need to test with multiple progress thread and devices. So currently we only have one progress thread. We also plan to implement and test the configuration without a dedicated progress thread. That is the case when all threads are calling the progress function and the send and receive operations. We're also planning to implement the backend using a lower level API, which is UCT, and possibly we hope to achieve some performance improvements from this lower level API. We also plan to implement the higher level LCI API directly using UCP and compare the resulting performance. So that is my presentation. Thank you for your time.
I wanted to comment that we added option to UCP worker to ignore a leak of a receive request to avoid this assertion. It's a new flag that you can pass when creating UCP worker.
Where's the mic? We're getting it. It's working.
So there is an option to deal with this receive request.
Yes.
Use your inner voice because we have no mic.
Yes, I'll try to send it a chat or over email.
Yeah, right. Yeah. I need to check this one because it's a very important issue.
Yeah, my general observations, there is mismatch between semantic, somebody taking verbs and trying to port verbs code over UCX. It's like, yes, there's no completion queue intentionally. Some features will be missing because of and it intentionally tries to expose higher level semantics and not low level semantics. Another comment that, yes, it seems like we have repeating requests for this immediate data, like Artemy with immediate completions. So yes, you have another customer asking.
Is this a confirmed bug or is it something that I'm doing wrong?
No, we don't have today. Intentionally, we don't export immediate completions in UCX and something that a couple of users requested.
Oh, okay.
The idea is that we'll be probably will be exposing.
Mm. Okay.
I have a question about that protocol layer that you have. You showed a slide and you mentioned that the decision between eager and rendezvous is done at the upper layer. So the question that I have is, when you decide to explicitly use the eager protocol and then you then use UCP in your backend layer, shouldn't you do something to make sure that if you're using eager, this doesn't translate to using rendezvous in UCP, or the other way around, and you're using rendezvous or UCP might use another protocol? And also to avoid like extra copies in UCP itself, because you are already doing some copies for your own local completions. And when you pass that to UCP, it could be the case that UCP also does another level of copying.
I think in the implementation, there's in the UCP layer, there's a flag that says force eager or force rendezvous. So that's so that we can basically explicitly choose which protocol we're using in the UCP level.
And then how do you avoid the copy? So let's say you decide to use eager, you force eager, and you've already done a copy yourself. You pass it to UCP, UCP does another copy. It seems like a duplicate work that is being done. And why not leave that decision of eager and rendezvous to UCP itself when we already have that copying, when we already have that decision making, and a lot of other things that upper layer I think is taking care of or has to take care of if they're missing.
Yeah. So for the potential extra copy of UCP, yeah, we currently have not dealt with that situation. So this is indeed a point of improvement for our implementation.
Okay, and how does this work for GPU buffers? Would the decision making be the same?
For GPU buffers?
I mean that you showed a picture that showed your eager protocol and some copy stages. So is that the same thing that will be used with GPU buffers as well, or is it just for CPU buffers?
Oh, it's just for CPU buffers.
So what happens with the GPU buffers then? If I pass a GPU buffer to LCI or with the U6 backend?
If I can jump in. So we currently haven't done much work with GPU buffers with LCI. It is a planned feature to be able to support that better. But there are questions exactly what the different runtimes we target exactly want out of it. Some runtimes handle copying in and out of GPUs directly and then assume that all communication is done from CPU buffers. Others handle it differently. So we're currently evaluating what different runtimes do in both for GPU and in general. And if I can answer the prior question about whether it's better to handle the decision making at the lower or upper layer. This was actually in the presentation yesterday about Realm.
Yes.
Then the request there was also to let the upper level handle the decision making about protocols.
Right.
And I think that's common among these runtimes. They want to be able to, they have a better global idea of what's going on, what resources are available,
and being able to have some impacts on the decision making at UCP level is good. But my understanding was that with LCI, you are actually building the protocol yourself at that upper layer. You're building your own eager protocol or rendezvous. With LANL, we would like to have the choice to select between these protocols from UCP, but we don't want to build them ourselves. That would be, I think, not the best thing, because we're sure that UCP can do that better. Yeah, that makes sense. So one other question that I have is, if you have time, I don't know, do we have time?
I think it's something.
Okay, so one other question I had is, what would be the motivation to use LCI rather than using UCX directly, right? Rather than using LCI as a layer that might use UCX or something else, why not implement? I think one of the examples that was mentioned was HPX, for instance, where LCI is being used. Why not use UCX directly?
Well, yeah, so I can help answer that question. So, yeah, so LCI, so right now it's a research tool to investigate what is a better way to design communication library. It's not necessarily like try to replace any of the existing communication libraries, because we don't have enough people, and we know that it's hard. So why not? So why use LCI instead of UCX? So yes, you can use UCX, you can use LCI. So we don't want to like really prove like LCI is better than UCX, but to see like if we design the communication library this way, whether its performance can be better. So yeah, if its performance, so yeah, it's more like a research project, like rather than a production like computation. If that answers your question. So yeah, maybe simply saying like LCI, the reason to use LCI is LCI might have better performance in multi-threaded case. And based on our previous benchmarking evaluation, it kind of does have better multi-threaded performance. And
well, my understanding was that there was a good amount of overlap between what LCI wanted to do and what UCP already provides. So, and I was trying to understand. Well, as a research tool, yeah, that makes sense.
It is possible to implement the LCI interface in a higher level using the UCX interface, and that's one of the future work we need to do to give a direct comparison between these two libraries. Right. But like empirically speaking, right now the coarse-grained blocking lock in the UCP worker has greatly impacted the performance. Has greatly impacted the multi-threaded performance. And that's one thing that LCI is definitely like doing better than UCX. Because LCI is directly built on top of InfiniBand, and it has separate lock for different data structures.
Yeah, which brings me to like my last question, which is I think for the UCX community mainly. So this UCP coarse-grained worker lock was mentioned in this presentation as well. I had my own issues when implementing the backend for LANL too. Do you think we should start thinking about addressing that issue, make the scope of that lock finer? Is there even a plan for that? Because it seems like more runtimes, more multi-threaded use cases are showing up, and this is an important bottleneck when it comes to using UCP.
Oh yeah, it seems like we have more and more cases where this is needed. It's not a simple change, but it looks like it's becoming more and more important. So I believe you have the similar issues with Legion, right?
Yes, exactly. Yeah. And even that the workaround that we have, which was using separate send receive workers, doesn't really address the problem completely. It just makes it a little bit better. But that locking contention is still there and is hurting performance.
If I could add a comment, not about the lock, but you were asking earlier about why not implement things using UCP directly. My impression is that the UCP feature set is largely driven by the demands of MPI, and inherits some of the limitations imposed by MPI. For instance, the requirement of ordered communications for on the same tag, that most of these more dynamic runtimes don't need or care for, because they're receiving messages dynamically in some fashion anyway. So they necessarily can't make assumptions on the order that messages are received. And so that they handle it in some other way. And by reducing by loosening this requirement, then you can get some performance gains. For instance, our ability to use a hash table instead of a matching queue. And it's not necessarily a reason to use LCI, because note that there is a significant amount of overlap, but is more of an idea of what how to drive communication runtimes in general forward to be able to better address the needs of these dynamic compute runtimes.
Yeah, makes sense.
For the other options that kind of encourage users to use other semantics, if you don't care about ordering, essentially use active messages that don't impose any ordering requirements. And this is what is used by majority of other non-MPI abstractions. It's active messages. There is no ordering constraints. You just get callback with the data, and it's up to upper layer to decide what they want to do with this. So do you think it's having active messages abstraction, it's not sufficient?
So yes, we can use active message construct to implement the backend like send and receive function, to replace the backend send and receive function. So that's essentially like implementing the LSI interface in a higher level, like with the UseX backend. So that's one of the future work. I think active message is a good thing, and we will try that later.
Okay. Thank you. Great discussion.
All right. I think we're gonna say thanks again to the presenter and then move on.
Great.
Up is Ofir. Are you connected?
Well, my name is Ofir. I'm a member of the U6 team from Israel. Today I'm going to present you with the Spark DPU project we are working on for the past few months. So this is the plan for this presentation. We'll start with a quick introduction to Spark. Of course, we're not going to speak 1 hour about Spark. It will be just a quick overview of the history, what is Spark, and what is MapReduced and Shuffle. Next, we will speak about the motivation for this project. I will then present you with our solution. Then we will go over the different components of this solution, and I will give a quick update at the end about the current status of the project. So let's do a quick history brief about Spark. So in 2004, two engineers from Google released an article called MapReduced, Simplified Data Processing on Large Clusters. They presented in this article model for processing large data sets distributed across many nodes, and they defined there some key ideas, and this article made a lot of noise, and two other engineers, Mike and Doug, read this article, and they thought it's very important and revolutionary, and they released a dupe in 2006. And in 2014, Apache Spark was released. Spark is a data processing engine, similar to Hadoop, but it has some benefits over Hadoop, like in memory processing. NVIDIA released a few, couple of projects that aim to reduce the time it takes to run Spark applications. First project was made by the ex-member of the U6 team, Peter. It was released in 2019. Peter implemented there a shuffle manager for Spark that use RDMA. He store each file in memory, so each data file had a copy in memory, and use UCX with RDMA to exchange data between the nodes. Of course, this solution has some limitations because the size of the data cannot exceed the total amount of memory in the cluster. So it was good for specific cases, but not for, it's not a general solution. In 2020, NVIDIA released Rapids for Spark. It's an accelerator. If Peter mainly worked on the shuffle manager, Rapids tackle the problem of improving Spark from different direction. They provide a layer that translate the Spark application, so it will be possible to run them on GPUs. So the user can write the application in the language, the framework he knows, like MySQL, and NVIDIA Rapids know how to translate this code to be run on CUDA. They use the new feature that was introduced in Spark 3 that enable scheduling of a task over accelerator, like GPUs and FPGAs. And they got a very big improvement in performance, and they prove that you can reduce the time it takes to run a Spark application, and This way you can also reduce costs by combining nodes with the GPUs. And in 2021, Peter introduced Spark UCX with active message. Not like in the previous solution now, the data is being read from the disk, and it's exchanged using UCX with active message. And now we arrive to 2023 to Spark DPU. So Spark DPU, it's an attempt we are making now to reduce the execution time of Spark application by improving the shuffle stage and other things in the execution of this task. And we are using a set of ideas and to build this solution. We are using a DPU. We are using UCX, of course. We are using a fast storage device, NVMe. And I will describe the architecture and the solution in details in the next slides. So let's start with what is MapReduce. MapReduce is a programming model for processing large data sets. This is taken from the article I mentioned in the last slide. The map and reduce are functions. If you worked with functional languages, you probably know the map and reduce functions, so it's pretty similar. Map gets a set of key value pairs, and it emits intermediate key value pairs. And the reduce function for each key gets the set of values, and it emits the result. It can be one value or a set of values. And the most famous example is the counting the words problem, counting the occurrences of each word in the large collection of documents. So you can see here that the map for each word, it emits the word and the number one, and the reduce function gets for each word the set of values that it's a set of ones, and it's a sum it and emit the final result for each word. And now let's talk about what is shuffling. So shuffle happens when data need to redistribute it across the cluster. By default, the shuffle relies on traditional socket-based TCP/IP communication. And when the size of the data is increasing, also the time spent on shuffling is increasing. One of the customers sent us these findings. They saw that when the data size increased, 13% of the time spent on shuffling, changing data across nodes in the cluster from the overall task execution. Of course, there is a big potential in improving performance if you improve the shuffling, but our solution is aimed for improving shuffling, but it also has the potential to improve other aspects in the executions of Spark applications. So I will go. This is taken from the article. Spark, it's from 2004, but Spark is actually run application in a similar way. You can see here a master. Today it's called driver in Spark. Workers are the nodes, and the driver assign tasks to the workers. It can be map task or reduce. And you can see here remote read. This is where the shuffling is taking place. This is what's called shuffling, read of remote blocks from remote nodes. So what is our solution? In the default Spark implementation, Spark is responsible both for writing the intermediate results and also to listen and reply to fetch block requests. So Spark is running a server that is listening to all the executors in the clusters, and each executor needs to run this server. And when executor receives the fetch block request, you need to read the data from the disk and reply to the requester, send him the data. This, of course, takes times and consume CPU and also involve many I/O. So our solution is to offload this work to the DPU. So the DPU will serve the fetch block request. He will perform the I/O read operations from the storage device, and he will respond with the data and send it back to the executor that requests the data. To do it, we need to split the work between the host and the DPU. So the DPU will write the data to the NVMe drive, to the storage device. He will update the DPU with the locations of the blocks. And when you need to fetch data from the DPU or from a remote node, you will send fetch request to the DPU owning these blocks. And the DPU will serve the fetch block request, like I described before. If you have any questions. Okay. So what we try to achieve, what we try to achieve here is, of course, reduce the time it takes to run Spark application. Why we think our solution will be able to do it? We can divide it to three different topics. Networking, we will improve the network capabilities by using RDMA. When running our benchmark, we saw that rendezvous write operation has the potential to improve network capabilities in this use case. So we are also planning to add this feature in the future to improve the network capabilities even more. And the number of connections with our architecture is far less than the number of connections, traditional Spark TCP needs. In Spark, each executor needs to connect to all the other executors in the cluster. And with our solution, we can reduce this number of connections. So it might also help reduce the network load. Storage, we plan to improve the I/O capabilities by using multiple fast storage NVMe devices, and improve CPU utilization by using DPU to handle fetch block requests and also progress the queues. All the IOs will be done by the DPU. And this is how our solution looks like if we split it into components. So let's talk about each component here. We'll start with the network layer because you're all familiar with UCX. So we are using UCX as the network layer. Storage, we are using multiple NVMEs. Actually, 2 in our case, but I guess we can increase this number. We are using the SPDK as a tool to implement our driver. SPDK is it's a development kit for writing the user space application for storage devices. And on top of SPDK, we implemented NVKV. You can say that NVKV is our driver for posting commands to the NVMe, read and write operations. But it's not like simple driver. It's have something special. We will talk about it in the next slide. JNVKV, it's Java bindings, so we can call the NVKV functionality from Java. And this is the components in the host. And in the DPU, we have NVKV again, but you can see here that I mentioned RDMA. Why we need RDMA here? Because to control we need to control the NVMe from the DPU. In order to do it, we are using RDMA operations from the DPU to control the NVMe on the host. I will get into details in the next slides. We also have UCX here, of course, and we have the Spark service that this is the driver, the server I mentioned before that is listening to fetch block request and perform the read from the disks and reply to the requester with the data. We also use the Cross-GVMI key because we need the DPU. The DPU is actually using host memory for the I/O operations for when he reads the blocks from the storage device. He reads the data to host memory, and later on you need to send this data to the node that requests the block. And in order to do it, we are using Cross-GVMI key. And on top of that, we have our implementation for Spark Shuffle Manager. We needed to implement both writer and reader in the Shuffle Manager. We also needed to define a protocol so the host and DPU will be able to communicate with each other. And I know it's a lot, so if you have questions, please ask. I will explain about each component in the next slides, but if you have question about architecture in general. Okay. So let's start with the storage. So like I said, we are using NVMe. We need both host and DPU to be able to perform I operations with this NVMe. The host is performing write operations, and the DPU is performing read operation. So how it works. So when the host need to perform a write operation, NVKV simply fall back to the SPDK functionality and the post command and call for completion. This is not a very interesting case. It started to become interesting when we look on the DPU. So the DPU also need to perform read operations. So it uses RDMA for that. How it's working? At the beginning, the host sends to the DPU information. What is this information? It sent to the DPU. It creates an Mkey for the address space of the control registers of the NVMe. It sends this Mkey to the DPU, as long with the addresses of the bounce buffers that he pre-allocated, and the Cross-GVMI key for these bounce buffers. And he also sends a translation table from virtual address to physical address of these bounce buffers. The DPU gets this, let's call it NVKV host context. And when you need to perform a read operation, he call SPDK library to construct the read command. He places the address of the host buffer block, and using RDMA operation, he posts the command to the NVMe on the host, and then he can call for completion with RDMA read. And this way, DPU can perform read operations from the NVMe on the host. Do you have any questions?
I have a quick question on this slide.
Yeah.
So how much intermediate data are we talking about? How necessary is NVMe? If we're already sharing memory, why not just read and write through that shared memory block?
You mean read the data from memory?
Yeah.
You mean store the data on memory and read it from memory?
Yeah.
Sometimes
why not do that preferentially, and then you can fall back to NVMe if you need to disk.
I didn't hear your last sentence.
Why not prefer to communicate over memory, and then you can use disk if it exceeds memory, but is it necessary, or how necessary is that?
Sometimes the you don't have enough memory to store the data on memory. So you have to use NVMe device, some storage device. In our case, we chose NVMe, but sometimes the data is much larger than the amount of memory you have. And this is answer your question.
Sure.
Okay. Any other question about the NVKV driver? Okay. We for our solution, we also needed to decide of a way to store the data on the NVMe. Spark is using a file system, is using files called the HDFS. We are storing the data as a raw data on the disk. So we needed to do two things. One is to split the disk between the executors because they are all running parallelly. And the second thing is to keep the block locations somewhere. Spark is using files, index files for the block locations. We store the block locations on the DPU in memory. So when the host is writing a block, and the block is identified by map and reduce ID, he writes the block to the NVMe in this executor private region, and then he sends a message and after the DPU with the location of this block, and the DPU keeps this information in memory, in a map for future fetch block requests. The host DPU protocol we defined. These are the message types that we have. Let's first look on the host to DPU message. So we have the NVKV context information. This is what I mentioned in the NVKV slide. The bounce buffer address and the lengths, the memory key for the IO registers, the NVKV, control registers, the translation table. All of this is being sent by this message from the hosted DPU. We have the blocks information. This is the locations of the blocks on the disk. And we have fetch block request. These are the types of message that are sent between host and DPU. Between DPU to host, there is when the DPU gets the NVKV context from the host, he reply with NVKV remote context to the host. And we also have a message to reply to fetch block request. It's actually the data with some identifier, so the host can trigger a callback when he gets the block. And we also implemented the new shuffle manager for Spark. In the previous shuffle manager, I mentioned in the beginning, Spark U6 shuffle manager, we mainly dealt with reading the blocks and sending them across nodes. This time we also needed to implement the shuffle writer, because we are writing the data as raw data to the NVMe, and we also need to update DPU with the locations. So we implemented the new shuffle writer. We also implemented the new shuffle reader. That what it basically does, it's sending fetch block request to the DPU in the host that owning these blocks, and wait for the data to arrive. And the shuffle manager at the beginning need to perform these tasks, initialize the NVKV, connect to the local DPU, and send all the relevant information to the DPU. You also need to connect to a remote NVKV on the DPU, and to establish connections with all other DPUs. So we needed to implement a way to share the information between the executors of the addresses of the DPUs, and also sync between the executors when they are start to run. And now I want to describe you the, you can say the full life cycle of messages and interaction between host and DPU from the beginning until send fetch block request is received by the host, received back by the host. So at the beginning, host sending the NVKV context to the DPU. We already mentioned it before. Then RDMA is used to control the NVMe. I'm sorry, NVKV context is sent. Then host is writing blocks to the storage device, to the NVMe. This is what the shuffle writer do. And it sends the location to the DPU. After that, it can be sent by the local host or remote host. This is why this message is in red. So this message, fetch block request, can be sent to the DPU by the local host or remote host. The DPU receives this message with the ID of the block. It goes to his map, and he fetch the offset and the length of this block on the NVMe. Using RDMA, perform read of this block, and then he sends back to the requester the data that he asks with the rendezvous operation. You have any question about this slide? Okay. This chart is very similar to the one we saw before. The one we saw before, you can see the specific order of the messages, but here you can see how it looks like when two hosts communicate with each other. You can see the executor start by writing the data to the NVMe. then when you need to perform read operation, a message is sent using UCX to the remote TPU. It performs the read to host bounce buffer, to host memory, and sends back the data to the host that requested this block. So what is the status of the project? The POC is running stable. What I mean by stable, we can increase the number of executors and the size of the data, and it's all running with no errors, very stable. Our setup is consists of 7 nodes. Each node has a DPU, of course, 2 NVMe devices, and more than 200 GB of memory. We are using, as benchmark, we're using group by test. Group by test is very simple Spark application. We chose group by test because it produces the data, so you don't need to download the data or find the data to run it. It also very give you full control over the size of data, how it's being split, how much you can control, how much map task it will run, and how much reduced task it will run, and it is very easy to run and control. I think the only downside of this test is that it's very network bound, and some of the benefits of our solution we will not see them in this specific test. So we are planning to add other types of benchmarks that are more CPU bound. Regarding the results, we are at the very beginning. We start to we have some results, but we still need to run more extensive tests to see that they are stable and consist. But I can say that it's look promising. We already see improvement in the read stage. And that is the first thing we aim to improve, around 13%. And we of course have much work to do to optimize this solution and other parts that are still not optimized. But you can follow Spark, use Spark DPU for future updates, and when we have results, I'm sure we will share them with all of you. So that's it. If you have questions or
any online questions? Okay, let's thank our speaker.
Thank you.
Okay, great. So my topic is Cross-GVMI UMR Mkey Poole, and to give some let me see why it's not moving forward. Okay, so to give some background information, the DPU or data processing unit has been a hot topic for the past few years. Okay, so when we compare the traditional server and the new DPU-based servers, the most distinct difference between the two is the NIC is now all of a sudden become programmable, right? So at NVIDIA, we also have our own Bluefield data processing unit. So if you compare NVIDIA's DPU, the Bluefield DPU versus the generic DPU, I would say perhaps one of the most important feature is the NVIDIA Bluefield DPU. It has a CPU, an ARM core CPU, and some of the memories on board, along with all the hardware accelerators. So what this allows us to do is that we can run a generic operating systems on these ARM cores, and then people will be able to log in to the ARM system, to the operating system, and then use whatever programming language that people are familiar with and used to program the DPU. This greatly lowers the entrance barrier to program the DPU from our perspective. So almost immediately from here, you can see we can offload some of the features like the infrastructure management, software-defined security, storage, and software-defined networking from the host to the DPU immediately. There are multiple ways of doing the DPU offloading. Okay, so previously, the one that I mentioned was just to offload the full system services from the host to the DPU. But you can also do some of the partial offloading as well. This is a small diagram that is how you do this. So the left side is how we traditionally run the application process on the host. But on the with the DPU offload, now we can split the application or sometimes the user application into two different pieces. We have one piece running on the host and then the other piece running on a DPU, and have these two pieces collaborate together to work on the same problem. This is very useful. For example, our collaborators at Georgia Tech, they are working on offloading some of the molecular dynamic simulations on the DPU by leveraging the extra ARM cores, the computer powers, and the memories on the DPU. Barcelona Supercomputing Data Centers, they developed the DPU, the OpenMP for DPU offloading, that you can literally offloading some arbitrary code from your original code to DPU without needing a lot of effort. So here at NVIDIA, the primary goal of our group is try to explore possibilities to offload the communications from host to DPU. The first target we choose is to offload the collectives. So we use the UCC, the Unified Collective Communication Library, as our base software stack. And then we try to extend the UCC from the host side only to extend it to the DPU. So we have the UCC running across both the host and DPU, and to operate and to progress the collectives on both sides. This is the programmer model that we choose to offload the UCC. However, to achieve this, I have to mention one of the most important features that we leverage from the Bluefield DPU in this particular case, which is called a Cross-GVMI memory key. The Cross-GVMI memory key, as you can see here, the GVMI means Get Virtual Machine ID, GVMI, or sometimes we can also call it a Virtual HCA ID. What this feature allows us to do is we can create a memory key on one of the virtual HCAs, and then by creating an alias memory key from another virtual HCAs, we can access the memories. That we register in the other virtual HCA. As far as both of these virtual HCAs, they belong to the same underlying physical HCA. Okay, What this means is that we can create a work request to reference the memory from another virtual HDA. So in this particular case, for example, if we create a memory key on the host side and create the alias memory keys on the DPU side, then from the DPU, we can post a work request on behalf of the host memory without needing of the host involvement at all. What this gives us is the benefit that we do not need to copy the data from the host to the DPU before we send the data. And after receiving the data, we also do not need to copy the data back from the DPU to the host. So this saves a lot of trouble. So we've had the pleasure to work with Joseph's team since last year to define the whole workflow and all the APIs from the UCX perspective to leverage this capability. Okay, at this point, I would say the workflow and APIs are pretty mature now. And in this slide, I'm going to show you how this is being done from both UCC and basically from the UCX perspective. So as soon as the collective is started on the host side, we first use the UCP map to map the user buffers into UCX. Okay. And then we can use the UCP memh memory handle pack function to pack the memory handle to pack the memory handle that is mapped previously, and then to before sending this memory handle to the DPU side for the following operations. So in this function, the UCP memh pack, if the cross-GVMI memory key is needed, then we will register it here. And then we send this packed memory handle from host to DPU. On the DPU side, again, we use the UCP map function to import this memory handle that's exported from the host side. And then if the alias memory key is needed here, we will create the alias memory key. Once the alias memory key is created, then we can use the normal UCP RKey pack function to pack the R key and then send it to a remote DPU. Or use the UCP endpoint RKey unpack function to unpack the R key which we received from the remote DPU before we use them to create the RDMA operations, such as the put or get, RDMA read or RDMA write. Once the collective is finished, we use the UCP unmap to unmap the user buffers from UCX. So this is a pretty straightforward workflow. However, when we first have this implemented and then put it into the user applications perspective and started evaluating the performances, immediately we realized the performance is not what we expected. Put in another words, in another way, it's far worse than what we expected originally from doing the DP offload. So we start doing the breaking down of where this high penalty or cost is coming from, and then we finally identify the issue comes from the memory key registration. Okay, so let's review how we originally, how the memory keys are being registered in the original implementation in Bluefield 2. In Bluefield 2, when we start to register the memory, first we have to register the user buffers via the UMAN registration. And we cannot use the IB-regmar to register the memory and then modify it to allow you to be able to do cross-GVMI access. So we have to do this through the UMAN registration. If we take a look at this breakdown table here on the right side, you will see the UMAN registration cost varies as we change the size of the buffer. Okay, and this can get to some very unreasonable numbers. For example, if we need to register 1 GB of memory, this will take like more than 114 milliseconds to do so. Okay, the unit here is nanoseconds. So once we have these user buffers being registered through UMEM, then the next step is we have to create the memory key from the UMEM registration. And this cost itself is pretty constant. It's pretty constant. And it's pretty much fixed at 160 microseconds. So after that, we will need to modify the memory key to allow cross-GVMI access. And this is this step. It changes slightly as we increase the buffer size. So basically, it varies from like 100 microseconds to almost 200 microseconds range. And on the DPU side, if we need to create a memory key alias, the cost here is varies from 180 to 200 microseconds. Okay. Of course, there's also deregistration associated within the code path. And the deregister of the memory key on the host side is roughly like a 140 microsecond-ish. And the UMEM registration, once again, it varies largely according to the buffer size, but it's roughly from like 74 microseconds up to like 2.4 milliseconds range.
Yes. I have a question. Do you mean the implementation where we use the direct UMEM before we use the UMR?
Yes, this is the UMEM. This is the UMEM. This is the older version of the UMEM. Okay. So from this table, we can see, okay, immediately we can identify one of the low-hanging fruits or the bottleneck here is the UMEM registration, right? Because this is going up to 114 milliseconds large. This is huge, humongous. So fortunately, we get to test the Bluefield 3 very soon. And then in Bluefield 3, the UMEM registration limitation was lifted. So we can use the normal memory registration via the IPv4 but we still cannot use the memory keys that were created from IPv4 directly. And we have to use an indirect memory key to point to the direct memory key created from IPv4 in this particular case. But if we take a look at the cost table here, we can see, okay, so we don't need to do the UMEM registration anymore. So we remove this large cost here, and then all the rest are pretty much the same. So because we are not changing any of the workflows here, and the only thing that we need to do is just replace the UMEM registration and then replace it with the IPv4 and then replace it and also add in the creating the indirect memory key to point to the direct memory key. So the cost associated with this is we remove the high cost on the UMEM registration, but everything else remains. But if you take a look at the table, now all of a sudden all these memory key creations and then modifying of the memory keys and then creating the memory key alias on the DPU, they are still pretty high. They are all multiple of the several hundred microseconds for each of the operations. Okay.
So there's no hit in the registration cache, right?
Can you say that again? I didn't catch your question.
You assume that there is no hit in their memory registration cache, since you count the actual memory.
There is the memory registration cache. This is something I'm going to mention in a few slides. Because the issues that we're dealing with is a lot of applications that they use a lot of temporary buffers. So when there are temporary buffers, each buffers are being allocated for just one use, and after the use for data transfer or something else, then it will be released. So the memory cache in that particular case, the registration cache in that particular case is not very useful. This is why we bring this up. So another mechanism that to replace the KSM mechanism that we used previously to create an indirect memory key is we can use the UMR memory key. The UMR memory key or the user model memory registration is a very special memory key that we can create it upfront. Basically, you create it as a dummy memory key or an empty memory key. And then you can use a work request that you posted to the send queue to register the direct memory key to the UMR memory key. Okay. So now let's take a look at the workflow here. So we first will register the host memory key, the host memory via the IPv4, and then we create the UMR memory key using the db create indirect memory key function here. And then we can post the registration work request through the regmr, the db-regmr API or the function. So if we take a look at this cost table here, creating the UMR memory key is still pretty high, several hundred microseconds high, but posting this work request or complete this work request does not take too much time. So it only takes roughly 1 microsecond-ish. And then all the remaining are still the same. And then destroying the memory key or invalidate the UMR memory key, once again, is a very lightweighted operation as well. So it's another 1 microsecond. Okay. So if you compare this workflow with previous workflow, there's not much difference at all, right? On the absolute numbers, the total cost is perhaps slightly higher than the previous mechanism. Okay, but what this gives us is the main topic that I want to bring up today, which is the UMR memory key pool, because of this unique feature of this UMR memory key that you can register it through the work request. So this idea was originally proposed by Gil to us from NVIDIA. And when we heard this, immediately we grabbed it. This is absolutely the thing that we needed. So taking a look at this cost, the workflow again. If we have the UMR memory key pool, then what we need to do is we can create a few of the UMR memory keys upfront. And then we can register the user buffers to these UMR memory keys on demand. Once the user buffers are no longer needed, what we need to do is just to invalidate the user buffers from the UMR memory key. And then we can keep the UMR memory keys alive through the whole life cycle of the application and keep reusing all these, very few of the UMR memory keys that we created upfront. Okay. What we can achieve in the end is we can remove the UMR memory key creation, the high cost, roughly 200 something microsecond of the cost. We can remove the host UMR memory key modification to allow it for Cross-GVMI access, which is another like 140 to 200 microseconds-ish. And then we can also remove the UMR memory key destroyed, roughly 150 microseconds, and remove all the costs on the DPU side. Both are roughly 150 microseconds above. Okay. And then the only thing remaining is we only need to register the user buffer. This is something that we always have to do. There's no way to avoid it, right? But the additional cost to that is just two of the lightweight operations to register the UMRM key and to invalidate the UMRM key, and both are just roughly 1 microsecond high. So this gives us the opportunity to remove or to save roughly 800 to 900 microseconds per memory key. This is very important for the applications that actually use a lot of the temporary buffers, which is something that we're dealing with very frequently these days. And also very important for the point-to-point operations, because if you take a look at this, the total cost, for example, if on NDR, thinking about if doing NDR speed, if we're sending like a 1 megabyte of data, the cost is only 25 microseconds. If we need to spend 800 microseconds to register buffer before we can do the 25 microseconds of the data transfer, that is a huge saving, right?
Okay, so Yong, I have a question.
Yeah.
So, if I said correctly, most of the benefit is for, let's say, a few megabytes or less, because then the registration is not so expensive. But on the other hand, creating keys and importing keys is the overhead of that is becoming more significant, right?
Yes.
I guess you have some kind of hash table, some kind of lookup instead of
Yes.
import on the DPU side.
Exactly. So this is the memory key pool architecture that we did. We implemented as a POC. So the architecture will involve some of the additional UMR dedicated QPs and CQs. We also need to create a UMR Mkeys, Mkey pools on the host side and a hash map, just like Yoshi just mentioned on the DPU side as well. So we have both. We have Mkey pool, which is implemented as a free list on the host side. When we also have a hash table on the DPU side. What this gives us is that we can reuse the registration cache that's currently being implemented in UCX. So we can use the registration cache on both sides. If the memory registration, if the memory region is found in the registration cache, then we will reuse no matter what, right? If the memory region is not found in the registration cache, then on the host side, we will try to retrieve one UMR Mkeys from the Mkey pool, if there's one available. If nothing is available and the Mkey pool is empty, we'll create another new UMR Mkeys. On the DPU side, if the memory region is not found in the registration cache, we will try to find alias from hash map. Okay. If the alias memory key has not been created on behalf of the host UMR memory key, then we will create a new alias and then put it into the hash table. So this is exactly what Yoshi just mentioned. However, with this very simple architecture and also very simple implementation, that we have to deal with an inevitable, unavoidable consequence from using the UMR Mkey, which is we have to deal with the zero-based virtual address region. Okay. So the reason for that is using this mechanism, the UMR Mkeys are created from the RDMA core API. It can only be used in a zero-based mode. So you cannot use a normal virtual address with these UMR Mkeys. Okay. So what this means is this is completely incompatible with existing UCX memory key management mechanism. Because in current UCX memory key management mechanism, there is no attribute associated with the memory key at all, right? So, in many of the cases, it's only being referenced as a 32-bit integers, and then being passed through opaque object from UCP to UCT. Okay. So then to accomplish this task, in the POC, the first thing that I needed to do was to expand the UCT IB MAN-T data structure to add the base address into this data structure. So I can have a reference to the base address whenever I need it. And then I also expand the flags to flag to add flags to this particular memory key. Whether this is an indirect memory key or a direct memory key, whether this is a zero-based memory key or whether this is a normal virtual address non-zero-based memory key. Okay, and then whenever that we need to pack the memory handle in the R keys, then we will also pack the base address and the flags along with them as well, so we can have a reference to those. Then when we're building the U keys, for the particular operation, for the RDMA operation, we will use the proper offset calculated from the base address when that's needed. Okay. However, even with this mechanism, there is still one caveat which is not so very easy to handle. That is the overlapped memory regions. Because in UCX, the current way that it handles memory regions is if there are two memory regions that with the pages that are overlapped with each other, UCX will try to merge those memory regions and create one bigger memory regions on behalf of the both. Okay, so if both of these memory regions they use the same type of memory keys, either they are both using the normal VA or both using using the zero-based VA, they are fine. But if we have if we have memory regions using two different mechanisms, then this will create troubles. So how to deal with this? In my opinion, there are at least three different ways to deal with. One way is what we implemented in the POC is we can do this from the top-down method. Basically, when we're posting the RDMA operations, we tell the operation whether we are going to use the cross-GVMI memory key or not. And then this will solve the issue. This method is very quickly implemented and very simple to do, but this is only for the POC purpose. So I do not guarantee this will handle every corner cases. So currently, I'm only patching it to do the RDMA operations that we need. Another mechanism that I think is possible is perhaps we can introduce a new memory type. Which is similar to CUDA or ROCm memory types. For example, we can perhaps add a cross-GVMI memory type, and then to manage them with different page tables within the registration cache. This will take a little bit longer to implement, but the benefit is it will be fully compatible with existing UCX infrastructure, including back compatibility. But it may incur some overheads to register the same memory regions with different memory types, because now we may have the memory regions that we sometimes we need to use with the normal memory type host, and sometimes we probably need to use the mem type cross-GVMI like that. A third mechanism, yeah, go ahead.
Can't we use a start address with UMR, or you say it's only zero-based? Is something specific to DPU or to cross-GVMI?
No, it's particular to UMR. This has nothing to do with cross-GVMI. We're just using the UMR, which is completely separate. If we
used at some point start address parameter with UMR, this can set the virtual address where memory access to that region would start.
I'm not sure if that's possible or not, because in that case, it sounds like that you are creating the one-time user UMR key, which is different than what we do here by registering the directed memory key directly into the UMR memory key. But if you said when we are posting the work request, you can set the start address. I'm not sure if that's doable or not, but I believe we're already doing that. But I have not checked on the RDMA core implementation to see if that's actually been implemented. But this is definitely something that we can do. Actually, I do list it here. If there is a way that we can deal with these UMR memory keys without needing the zero base, then we don't need this whole thing at all. We can remove this slide completely. And
actually,
the issues.
A few years ago, when we used experimental verbs,
we used experimental verbs that support this. Yes, I totally understand that. Yes, I use that myself as well. In experimental verbs, this is doable, but in RDMA course, I've talked to lots of people. I have not been able to figure out a way to do it without using the zero base.
Right. So, but even if it's not supported in RDMA core, it's not a problem. As long as hardware supports it, we can do it directly.
Exactly. Yeah. So this is why I listed the fourth option here. If there is a way to do this, then we don't need to. Right. But I still want to mention the third mechanism, which I think is a more of a viable solution to this. And not only this, perhaps to some of the other future features that we may want to consider related to memory keys as well, which is a new memory key management mechanism. This will be a new architecture that we rebuild from bottom up to manage the memory keys in UCX. this will be future-proof. Why I say that is because we're also thinking about some of the other memory key features, such as reserved L keys and Mkey by names, and other things that will require some different properties or attributes associated with the memory key, so we can understand what these memory keys is being associated with. So this, but the caveat with this is that we will need to touch pretty much everything. We'll need to touch almost everything from the UCP to UCT. So it may cause some of the API or even API compatibility issues. Okay, so backflow support will be in trouble. Okay. So last but not least, let's take a quick review of the performance. So to evaluate the performance with this POC, I had to modify the OSU auto V. So the original OSU auto V, it used a persistent buffer, right? So there's only one buffer and then use it for every iterations. So I modify it to use the temporary buffers for each iteration. And this table shows the performance comparison. The blue curve is the host only with no offload. This is the baseline. Okay, so all the other three are using the DPU offload, and the red one is the original UMAN registration mechanism. And we can see on medium-sized messages that we're doing good comparing to the baseline. But when the message size is big enough, the cost just shoots through the roof. So it's not very useful at all. With the indirect memory key mechanism that we currently have in UCX, this is much better. Okay, so everything that we tested in the range, they are always better than the baseline. And the last one is the green curve by using the UMR memory key pool. So you can see on large messages, they are comparable, actually very close to the indirect memory key mechanism. But in medium-sized messages, we can be like almost 34% better at 16 kilobytes and then 17% better at 32 kilobytes. Okay, so the performance advantages that were obtained here is can be determined by the registration cost versus the communication cost. Yeah. Okay, and another good thing with this mechanism is there is no over provisioning of the UMR keys. Okay. So as a quick summary, the Cross-GVMI memory UMR memory key pool is a highly desired features for pretty much all the HPC applications that we are dealing with today, which we see benefits from using the Cross-GVMI to do the offload. Okay, this concludes my presentation. So if people have other questions, I'm more than happy to work with, and we'll also will be happy to continue to work with the UCX community to get this feature into the UCX implementation.
Any questions?
Sure.
So I just wanted to comment that Yong, thanks a lot for this, and we plan to take this POC and upstream it to UCX for next release. It looks very useful.
Yeah, yeah. Thank you very much. Yeah.
So I'll go ahead and just start then. So I'm going to spend a little bit to present some in-progress work on message aggregation. So there's a paper that I'm expanding upon that I'll provide a link for at the end that introduced this aggregation context, and we were trying to expand upon it. So let's just get right into it and give a little bit of the background to build up on what's going on with that. So OpenSHMEM, as many people here may know, is it's kind of a simple low-level PGAS interface. But a number of common access patterns that we may see in applications with it can easily end up congesting modern networks with large amounts of small messages. In order to kind of get around this, it can require substantial rewrites of code using traditional approaches. So we want to try to avoid that, especially for a lot of older legacy code where there's not much interest in that. So the aggregation context I mentioned, as it existed, as it always exists right now, it was introduced to allow point-to-point messages, puts, gets, atomic operations, to be deferred and then later sent in bulk. So they just kind of get queued up, and when they get filled, they get flushed out. I'll get to that a little bit more in a bit, but we are able to get already in simple cases, we are able to get up to 65 times performance improvement. That's not a typo. That is 65 times. However, in adding that implementation, we saw some deficiencies where when we got to more complicated scenarios, it's wasn't as clean to be able to provide a nice way to be able to defer without getting some more of those rewrites. So we want to be able to address dependencies between operations where we maybe fetch some data and then later want to reuse it for something. So what we're kind of using here as a critical measure for things is something. There's something called the bail effort. It kind of exists more or less for this purpose, to find key access problems that are challenging, and it also provides a number of applications that you can use to compare those with different implementations, particularly by also providing its own aggregation library called conveyors. And that's what we're using under the hood, is we'll be using these conveyors to implement these aggregation contexts. There's more, but there's some notable examples of these bail applications include histogram, index gather, and the big one we're going to be focusing on today is sparse matrix transpose. Conveyors themselves, we're not going to get into the nitty gritty, but they're basically like stateful message queues. You push, you pull. It's sort of implicitly two-sided, but if you follow just a simple contract that it outlines, then everything is guaranteed to complete eventually. You just have relaxed constraints. So how the aggregation contexts kind of look, they expand on an existing enhancement to the specification from OpenSHMEM 1.4 that introduced communication context. They were originally meant kind of more for isolation between threads. And they so they're used to kind of modify existing RMA calls and similar. So you can do say a put to put out some memory to a remote PE with respect to a given context, and now that could be isolated separately from messages on other or the global context. So what I did was I added an extra option for the context creation that can specify, well, this context we want to be aggregating messages, and that kind of implicitly changes the semantics of communication calls to relax completion. So it's no longer guaranteed that it will reach a particular state of completion, like it did before. In fact, ultimately the remote completion is only guaranteed upon calling a quiet or basically flush for the context. But as it stood before, generally the input buffers would still be reusable. It would make copies. Internally, the information for operations, due to constraints with conveyors, everything is stored in fixed size structures. So we'll have the operation type, parameters like the local and source address and values. We put them all into a single fixed size structure to define any communication operation we could conceivably have. And then we just all put that in the queue and have a progress function that will automatically internally go through and incoming things. It'll see like it says it's this type, so I need to do this with this, and maybe send the response. So the big thing I mentioned that we're going to be focusing on here was sparse matrix transpose, and that's because this was the first application within Bail that we came across that kind of started to show some holes where maybe we needed some improvement. So what this does is it computes obviously it computes the transpose of a sparse matrix, but this sparse matrix is in compressed sparse row format, as we see above. So that's one of the things that makes it a little bit trickier to manage within an application, because we have sort of a what would seem maybe intuitively as like an uneven layout for how many elements from which rows or whatever are owned by a given processing element or rank within the system. But this is a very important algorithm for us. It's used a lot in machine learning and data analytics. But it's difficult to aggregate due to synchronization within the PEs for determining where to write the data. So let's look at it a little bit more. So the first, it's kind of got two phases. The first phase uses the histogram pattern I mentioned to basically just gather information. It wants to find the number of non-zeros in each column so it can know how much memory to allocate for the second phase, where we do the real work. And then the second phase needs to require for each element, it needs to require the new location and then write it to the destination PE. So AIJ becomes AJI or AT for the transpose, right? So kind of to look at the actual code, the phase one is very simple. It just looks like this. And on the left-hand side, we have the traditional OpenSHMEM code that we would write for this. We're just having a single loop. We're doing increments on column counts essentially. And so for each of those, we're going through until we reach the end. But the aggregation context, the only change that we really see is that now we have to have the extra quiet to ensure completion before the barrier at the end. And the increment becomes a context version of it. But that's it. Nothing else has to change. And that's the key focus we've had from the start for these aggregation contexts. We want to have it be as minimal of a code change as possible while still, providing dramatic performance improvements. And that pattern that we just saw with histogram, this is where we saw the 65 times in performance improvements I saw. It's like it's a dramatic increase. It's really great. It's really smooth. And this was run on 32 nodes from the HPC advisories Iris. And it performs really well. It has a little bit of a issue at the end, which it's a known thing. We just have I didn't go into it. If you want more details, you can see the paper. But the increment operations are packed in a second level, so that each one of those fixed size structures will have multiple increments. And how many increments we pack into a single structure is something that we can choose. Basically, the number is lower than it might be ideal here, and that's the only reason we even cap out at all here, really. But then if we look at the phase two, that's where things get a little bit trickier. So again, on the left, this is where we're starting off, but we'll see that now we're trying to fetch a value, and we're trying to use that value within subsequent operations. So we're trying to get a pause variable for the position, and then we're trying to use it as an index into a non-zero array. And that's problematic. We can't just do that, because if we defer and the fetch and add isn't complete, then it's by the time that we're trying to actually queue up the put, we're going to be capturing a stale value, not the value we're actually trying to retrieve. So originally the context implementation split this phase into two different parts. So we have a sort of a loop fission kind of approach. And if it initially does all those fetches to just one big position array, and then it does a quiet, and then proceeds from there to do the other half of the original loop to go out and operate on those values. And it works. It even provides decent performance improvements over AGP and even relative to conveyors up to a point. But we can see that the performance kind of plateaus pretty early on, and also the constraints that we added for the position array were less than ideal because we use up a lot of extra memory, and we would prefer not to have to do that. It's a non-insignificant amount of additional memory to do that, and it's worth noting we can, in theory, make some improvements to that performance with instead of getting the position array for everything, doing every fetch and add, we could kind of add another loop here, and we do say 1,000 fetches, and then we operate the puts on the fetch data, and then we do 1,000 more fetches, and we could do things like that. But each time we do something like that, we're adding more of the complexity, which is again going back to that substantial rewrite that we don't really want. So now we kind of see what the problem is. We want to kind of get these results, a get or fetch and something, and we want to be able to then use it for a later RMA call or similar, but we have issues with that. So what if a fetch value is used for an entire inner loop that we may have? Or what if we fetch and then use it for an inner loop, but inside that inner loop we have another fetch, and then that's used for another inner loop, and so on. We can't just keep splitting these loops out like we did before. So we want to be able to recognize when a data object associated with a pending fetch is used in subsequent operations, but also we want to defer the capture of that value so that we can maybe get that when it's actually filled in properly. And in particular, we want to note what if an application uses it for more than just OpenSHMEM calls. So it's valid within OpenSHMEM to just access the memory being pointed to by a symmetric data object directly, which is actually what we saw before when it was being used for index calculations. So we want to be able to also defer generic code until the values are fetched as well. So how do we kind of address this? We're looking at basically two different things. So the first thing is we want to be able to track the outstanding get operations. So you start one, we're going to have to keep some metadata to track it so we can see when it may be used again. Essentially, we're sort of creating a sort of pseudo handle, like it's a non-blocking handle for the operation. And we do this without any additional changes by just writing into the destination a variable, because it's invalid to be accessing that until the operation is complete. So we can kind of do that, and we write an index into a temporary table that contains the metadata that we want. But that table also has to also have the address of the buffer, point back to it, because the variable may just happen to have what would look like a valid address in it. We have to actually know if that's us that put that value in there or if that's actually its regular value. So if we later see a use for an address that is associated with a pending, or that we think may be associated with pending value, we can verify that by checking that address. Upon use of that value, then we can we can capture the parameters the arguments for the operation that's using that value, like a put, and store that in a queue so that we're not actually putting the put or the increment or whatever we may have that uses that fetch value. We're not actually processing that until later. If that queue reaches the maximum size, though, we may have to force progress until the dependent operations are complete. And then finally, when that response is processed, we can clear the metadata and store the final result, and we're done. So now we can do something like this, and this actually works. So this is now actually valid code. It can work, complete successfully. What's going on is that each, we just have this loop, and each time we're getting a get, it's putting that onto the conveyors that underneath. So it's actually something that could potentially be going out on the network, but it's not received a response yet necessarily. And when we get to the put, we see that we're trying to reuse that local array, local I, and so we can check is that value actually complete using the same strategies from before. If not, we just save the arguments for this put. We also save, hey, this is also a put. We put that on the queue, and then we move on. Eventually, when we progress, we get a bunch of responses. Once we fulfill some responses, we check that queue. Anything that can be executed, we then execute that normally, and it's fine. But we cannot do this because what we're doing now is we're using the value of local I as an index into some other array, and we don't know, coming into the put call, we don't know that the address of local I was ever used for any of this. So that's no longer good. We need one more thing. So we want to be able to have lazy execution of general code that can use those results. This is kind of similar to tasks, but maybe watered down a bit. So this could include things like what we saw before. We can use it as an index, or we can just access and modify the value directly. Any of that stuff could be problematic, and we need to have this lazy execution for it. So one of the things to bear in mind with this, though, is that unlike before, instead of only one dependent operation we may have any number. So we may have, say, a loop, and it's using the values of 3 different variables that we performed a get for. We also have to bear in mind, when do we want to capture the non-dependent values? That is things like loop indices or just regular local stack variables. We can either be capturing things on the task creation or on its execution. We need to know what that is going to be. So for looking at how we be able to accomplish something like that, we note that OpenSHMEM actually has it has its own compiler, which traditionally it's really a wrapper, but it's got its own OSHCC, just like MPI with its MPI-CC, and that's what we are supposed to use to compile your programs. So we can actually include modifications to the compiler in the form of modules and such to modify that behavior, and we can introduce a small pragma API for deferring statements or blocks. We're calling that right now just pragma-shmem defer. Dependent operations can then be explicitly specified as arguments to the defer clause, or just automatically inferred. And fetched results from an OpenSHMEM call are by default captured on execution, but optionally you can capture it immediately. We'll get into that. Stack variables like just a local unrelated loop index that you may be on, that's by default captured when you're initially creating that task. But you can also say this is going to have a lifetime that will last until whenever you'll execute this, and say capture it whenever you're actually going to run it by using the shared clause. And similar to before, we have a pending queue of these pseudo tasks, except that their release from the queues requires completion of all dependent fetches, so we have to check each one. So what this would allow us to do is, if we look back to the sparse matrix transpose that we had from before, now we can rewrite the traditional atomic gets and puts code into what it looks like on the right. So similar to what we saw for the histogram, we have something very simple and straightforward for the fetch. Nothing complicated there. We just use the context version, and then the only other thing that we have to do is we have to wrap the dependent code, which is the put and the if statement here, into a code block, and then add the pragma-shmem defer. Now, I said that I would be getting back to the what I was mentioning here with the capturing results of the fetch results within the immediate clause, because we're doing that here for one reason, because we note that we're using a static variable, just a single one. So we're writing to the same address each time we're doing an iteration here for the position value. Now, if we did what we had before, where we had just a large array, then we wouldn't need to have this immediate clause because no fetch would ever be writing to the same location that another fetch would be, and it would be fine. But in order to save on that memory, we would like to be able to just simply do what we might, something that might actually look more like what we would traditionally do on the left here, and we might want to just write that to a single place. But now, whenever we execute, we'll be execute a bunch of tasks that use the same value from whatever the latest fetch was. So this is basically how you get around that. You can say immediate on pause, and that just says whenever the response for the fetch for pause is completed, you immediately at that point copy the value into the dependent tasks, and then it loads it up properly when it executes, and everything's fine. So as we can see, we're back to something that looks really nice. There's almost no changes that have to actually be done, and you can get the automatic deferment, and everything continues going on from one iteration to the next just fine, and it only actually progresses operations when queues fill up. So this is a work in progress. The design, we think the design looks progressing, but we're still in the process of revising things, in particular the pragmas for if we want to maybe add some new clauses or something. We expect for there to be a complete implementation of the defer pragma for LLVM initially, but then eventually we expect there would be GCC as well. Currently, all testing is being performed on ORNL's Frontier, and in addition to the transpose, we intend to use this to finish off the triangles application, which is another. It's looking for. It's operating on graphs, which is another Bail application that had the same kind of problem, but that did actually have the nested aspect I mentioned, where we have multiple nested loops that each fetch values and then use it for another loop. And eventually the goal is to reach a completed topological sort. So finally, there is I will also mention there is some related work that also attempts to do some aggregation within OpenSHMEM. It's called this is recently published work that was called OpenSHMEM queues. It introduces a new API for explicitly pushing and popping messages onto queues, which requires more changes to the code, but it does also allow the ability to have quality of support for prioritizing some messages over the others. But at the cost of that, it's a more transparent API. You have to have more of that modification of the code that we were hoping to avoid ourselves. And in particular, currently there's no way to be able to support deferred execution of entire code blocks like what we're looking at here. So that's my work. I can open it up to any questions if anyone wants to ask more about something.
Any questions from OpenSHMEM community? Any questions online? So what is the plan for pushing this to OpenSHMEM standard? Has been reviewed by community?
I think we'd probably be waiting for more of a full-on open review once we get to at least some preliminary version of the plugin for LLVM to actually implement the pragma. We were initially thinking that we might be able to kind of speed things along and make it be able to be reviewed a little bit faster by just using macros instead, but then that comes at the cost of we can no longer inline the code. You have to actually take that block of code and move it out into a separate function. So we really want to be able to have the pragma instead. I think having, since it's important for the specification committees to be able to have working prototypes for things, I think we really need to first finish getting a complete and stable plugin. But then, yes, we want to, we very much want to immediately turn around and then put that forth to the community for feedback to see if we can kind of push that and maybe get it accepted into the specification.
Thank you. Any more questions?
Okay. So my name is Mikhail Brinskii. I'm one of the UCX developers, and today we'll talk about wire compatibility in UCX. I will elaborate a bit more what we mean by wire compatibility in UCX and what we do to support it, and what are our further plans. So wire compatibility actually means that it is possible to use different UCX versions for different processes. So for instance, I think it is quite important in cluster and cloud environments, where it is quite typical situation when software on the management node is not aligned with software on compute nodes. And what we would like to support is that it's still possible to communicate between management and compute nodes within UCX, even so UCX versions do not match. And UCX is actually wire compatible since version 1.14, which means that if we take some application and run it with current UCX version like UCX 1.16, then it is supposed to work seamlessly with any client running UCX 1.14 or 1.15. And also, it's even wire compatible since version 1.12, but with certain limitations, like only network transfer should be used, and there are other limitations as well. And our strategy now is that we support up to 4 previous versions of UCX. So if we are talking about version 1.16, which we are going to release soon, it's supposed to be wire compatible up to version 120 or 190. So that's our goal, to support 4 previous versions. And actually, if we elaborate a bit more, what means wire compatibility in UCX, actually what is very important is that protocol headers are compatible, which means that if you want to modify some protocol like rendezvous, eager, or whatever, you cannot just add some fields there, because it will not work. It will not work with previous versions. So whenever some protocol needs to be updated, it needs to be done in wire compatible way, and I will show later how we're doing it. Another thing that we cannot just simply change default values for configuration parameters, because UCX doesn't support setting different configuration parameters on different processes, at least for some of parameters. One of the good examples here would be InfiniBand segment size, because if different peers, they define different InfiniBand segment sizes, they will not be able to communicate. And also, we have a connection, a quite complicated connection establishment procedure. And during that connection establishment, we rely on the fact that different peers use the same algorithm for evaluating performance capabilities of the underlying hardware. And therefore, peers, they take the same decisions on what transports to select and for what protocols, etc. If we change this protocols and different peers select different transports, we also may end up in a certain error, which I explain a bit later. So regarding protocols compatibility, currently we don't have any addressing versions or any kind of flags and protocol headers. So it's not possible to distinguish what is a version of the protocol when we receive some message like rendezvous RTS or something else. We cannot just check what is a version of the protocol. Instead, we just added protocol UCX version to the UCP worker address, which means that every peer will know what is the UCX version of its remote peer, because it doesn't matter what connection establishment scheme we use. Would it be connect to worker or client server connection establishment? Anyway, both peers will receive a remote worker address, and that address will contain a version, UCX version of the remote peer. And based on that, we can make a decision whether the remote peer can support a new version of protocols or some new protocol. For instance, if we want to update just a single protocol, we will have to treat it like something newly added in this release, and it is shown on this slide. During connection establishment, we exchange worker addresses, and then we can see what is the peer version. And if peer version is the same as ours or even newer, we can initialize what we support. Otherwise, we have to stick to what we used to have before that to make sure that our peer can handle it properly. So that's how we did it for protocols compatibility. And I also mentioned our connection establishment scheme. And here I show an example where different peers select different set of transports. For instance, if we modify an algorithm of selecting a particular transport for a connection, for instance, we modified how we calculate performance of certain protocol for certain transport or something like that. And we end up selecting different transports on different peers. Then if we connecting if these peers connecting to each other simultaneously, we have kind of head-to-head resolution of connection requests. And we will select one of those, that's not a problem. But it ends up that we already selected something on our local side, and we receive a request from the remote side which doesn't match our local selection. And currently, unfortunately, UCX is not able to handle it, and it fails with an assert, which I can show here. So it is quite famous assert. I mean, a couple of bugs were reported, not a couple, many of bugs were reported about this. And it's also related to wire compatibility. I mean, if we change this lane selection scheme, so we may break it. And now we also can preserve wire compatibility when we modify lane selection scheme by also inspecting an address version. So we always know an address version of the remote peer. And if we would like to do something differently, we just need to be sure that the remote peer will do the same, which means that it says that its UCX version matches ours or even newer. So the same approach is used here. And we also added quite a lot of tests for wire compatibility in our CI PR pipeline. So for every PR, we run quite many tests. We're using UCP client server and Hello World applications. And we're actually running them client and server with different UCX versions. And we're running with version 14, 15, and now 16. And when we release further, we can add new versions. It's just one line change. We'd like to do it to be added automatically, but it's not done yet. Also, we're running it on different setups to make sure that we cover different hardware. And we run it with different settings, for instance, only with network transport, so with shared memory transport, to make sure that that this connection establishment scheme is tested well enough. And for those who is interested in this test and how we test it, I listed a couple of links here with our test, how we do it. And what we are going to do further, I think the most important thing is that we are going to support endpoint reconfiguration, which means that even if different peers transport selections do not match each other, we will not fail with the assertion, but we will accept the request from the peer, and we will initiate those transports which peer requested. So it's not that easy in our code, and it's planned works. We're working on that. And I think this will solve a lot of problems with wire compatibility. And also we're extending our wire compatibility testing to cover not all, but at least most of the wire compatibility issues coming with new PRs. And I was fast. Questions?
This is great. No questions. We need to start. Like I'm working environment where it's guaranteed that we're not going to have the same UCX version. Like it's very common in cloud environment. Like rarely you do updates, like cluster style. It just doesn't happen. So it's kind of features viral compatibility. It's must to have for production.
Okay. Maybe what we may discuss it whether you are satisfied with our goal to support just 4 versions of previous releases. So that's our current decision, but would like...
my ask going to be to support infinite number of versions back because it's wire protocol, and we do see. Just looking like Moffat install versions, it's like qualification time of certain stack have really long tails, right? From, the moment people release to the moment actually it's used in production, it can be a year, right? It's qualified. So
for versions,
for versions, just 1 year.
Well, it's about 1.5 years, but I assume that this limitation is not going to be forever, because it takes some time it's like a balance between getting things right and keeping things compatible. Hopefully at some point it will be extended to bigger, because we need, in order to make things more compatible, we need to change the wire protocol sometimes to make it feature proof. So
I would rather prefer not an old change, but like every 3 years or something. Year is kind of. I'm definitely like just looking at other software stack we kind of deploy. I'm definitely see, hey, this is Moffat version blah, which is probably 1 year old at least. That has been validated in production. This is what we're deploying in many systems. So I see kind of this very tail latency longer than a year for sure.
Yeah, I think we have to discuss it then. If you can make a clear requirement, like how many years or how many versions we can consider.
I would say minimum 2 years. This is the minimum that makes sense. And like for you guys, I don't know, like if is not including, you know, version in the header, Yossi.
We have.
So why you locked for years?
It's a different reason. If for example, want to change something in one of the structures that is going on the wire. So we want to introduce maybe some new version, like address version 2, for example, like we did.
Okay.
And so our strategy currently is first to support receiving the structure. So the current version would be able to handle a future version. And then switch to sending that version, a new version of the protocol by default. If we had to keep compatibility forever, we could never send the new version on the wire because it would break all versions. But having some kind of limit on the compatibility allows to gradually transition into newer wire protocol.
So your problem not the wire protocol, but what gets in data structures and wire protocol, because you have to keep a bunch of legacy if you have to deal with like all structures and so on. Which becomes difficult.
Well, we cannot send something to a remote peer that the remote peer is not ready or able to handle.
There is was paper from Google a while ago where they updated where like protocols on the fly. Essentially, they had a feature where
code injection or something.
Yes, binary injection. Essentially, when you establish communication, you detect all version. You actually can push library that will handle
or some data.
It's similar to what we did in paper, but like I not suggest to push to this.
Update on the fly.
Yes, you can update on the fly. If version mismatch, you can push. Like dotted
so do RM minus.
Yeah, you can push dotted source that will.
So I see a question from Jim about the notion of long-term supported releases. I don't think we have such notion currently, but if there is a requirement, we need to discuss it.
I'm not trying to introduce a requirement necessarily, just as a possible solution to what Pasha was talking about. Right, it limits the amount of cross-compatibility testing that you would need to do. You could keep it to the 4 most recent releases plus, you know, some number of long-term supported releases.
I think if we have long-term support, it means that we can never send a new data structure on the wire, as long as that long-term support version is alive, because it would not be able to handle the new data structure. One of the things that we're doing now is during the address exchange, we pass the version number, so it's possible to know the remote version and avoid sending things to it. Another thing we're planning to do is when we introduce new protocols, for example, improved rendezvous version or something like that, we are going to enable that protocols depending on the remote version. So if you have a older remote peer, we would not try to execute something with, we had put with signal, for example. Put with signal implementation would have to be disabled if the remote version is installed.
Maybe, I don't know, maybe you can keep some, some base protocol. But again, if you change structure, I can see how it's like you'll break a lot of things. Structure sizes.
The structures, it's not just what we send in packets, it's also things that we back and user have to pass, like remote keys, address.
And that's it, I guess.
I had a question about reconfiguration. So as far as I understand, endpoint reconfiguration happens at the very first attempt to have endpoint connection establishment. Is there reconfiguration after some exchanges have happened because, say, a device went down? Like, is it possible to have reconfiguration having detected that?
You're talking about some sort of high availability now.
Right.
Yeah, it's not related to what I was talking about. I'm not sure we have any plans for high availability support, but Yossi may correct me if I'm wrong.
We can say that the high availability support is going to have to come after a reconfiguration support.
Yeah, but do we have any plans for it? I mean, okay, we implemented and we supported endpoint reconfiguration and
Yeah, there were some ideas to do that. Obviously, it would be good for several users. Currently, because of complexity, we're doing other things for that.
I mostly brought that up in the context of wanting to check what Proto V2 would end up doing when there's reconfiguration after the endpoint has already been configured, because I believe the
would be error if there is some error on the device. The server side would detect peer failure. I mean, assuming that we enable the error handling feature on the endpoint, it would detect peer failure and break all communication with that broken peer.
I see.
On the other side, it would be probably some kind of fatal error.
Okay. Thanks.
Any other questions? You're online. All right. Thank you, Mikhail.
yes, thanks.
So, hi, everyone. My name is Shachar. I'm from the UCX team. And I will present today a feature that I was working on lately. It is called dynamic transport selection in UCX. Okay, 1 second. The agenda I'll start by presenting the problem we were facing, describe what we tried to solve, and we'll go to the design goals, which will try to describe the thing we had to think about when we reach the solution. Then I will go through the solution in details, and at the end I will talk in detail about the benchmarks that we use to test this feature. Okay. Can anyone see the presentation?
I think you're sharing the PowerPoint and not the presentation itself.
Yeah, if you can switch to
we actually see the first slide, so you need to switch to presenter view and share the correct screen.
Oh.
Well, now it's
not this one.
It's a multi-monitor problem, not this one.
1 second. Okay. So stop the share and reshare. Can you see it now?
It's still the full slide deck.
Can you see it now?
Yes.
That's right.
Yeah? Okay. So as I said, agenda, I will go through those things, problem statement, design goals, solution, and benchmarks. What we were trying to achieve, we tried to target large-scale scenarios in which we have a lot of endpoints or connections from a lot of nodes. Each node has a large number of connections to all the or some of the other nodes. In this kind of scenarios, usually we would prefer to use DC transport because DC transport is more optimized for large scale scenarios. It has better memory utilization usage as opposed to RC in that case, which has a high memory consumption due to the initialization and usage of one or more QPs per connection. The ability of DC to share QPs for several connections is better for us usually, but there are some scenarios, and here the problems begin, that they are not symmetric, which means there are a small number of connections which are more heavily have more heavy traffic going through them, other than in comparison to the other endpoints, which has less data and traffic going through them. So those scenarios where we have few endpoints which have a lot of traffic can be optimized if we know to identify them and switch them from DC transport to RC transport, because RC transport is has better latency than DC. So what we basically want to achieve is the ability to dynamically switch the transport of a specific connection from DC to RC while the system is working. So we need to notice that we have limited RC resources. For example, we can define a maximum number of 20 RC connections that we want to use per node. And the reason is, of course, memory consumption. We do not want to overuse the memory. So what we want to do is we want to identify the, let's say, 20 most high traffic connections in each endpoint and switch them to RC. So moving on. So what we needed to notice in this solution is a few things. First thing is avoid frequent switching, which means we do not want to overswitch. We do not want to move from RC to DC and RC again too fast because it will cause performance degradation. We want to limit the switching. This is the first one, the first issue that we want to deal with. Second is, of course, do not impact fast pass performance. Some of the some of the logic would have to be implemented on fastpass, and we want to do it in the best possible way without impacting it. We also want to maintain and keep low memory usage. Okay, we talk about scaled scenarios in which we have a large amount of connections. So we want to somehow gather information about all those connections without adding extra memory per connection. And we want to keep protocol semantics. For example, we have an active message protocol in which we want to keep the order of messages, and without the switching process impacting the order. So, for example, if we consider two methods for EP for how to track activity of endpoints of connections, we have one method would be to store some extra data per connection per UCP EP and use it as an index to access some global endpoint array which stores the most high traffic connections, and the other method would be to use a hash table, a global hash table, which will which we can use to which then we can use we can use the EP virtual address to access the certain entry in the hash table, and it what it means is that we do not need to store any data per any extra data per connection. So if we summarize, there is a trade-off here between performance on the first solution and memory on the second solution. So moving on, I divided the solution to three main parts. Each one has its own solution and its own things to think about. The first one is identify highly used connections, which means how exactly we identify those connections that we need to switch. Second is negotiation, which means in the network perspective, we need all the nodes to agree which connections should be switched. So this is another issue. And the third component is how to switch transport under traffic, because today, until today, we only decided which transport to use in the beginning of the system. Okay, so so here I gave the first potential if solution, and I will explain it, and then I will explain the issues with it. So if we want to evaluate each connection by counting how much data it sends, then the simplest solution would be to add a counter per connection, which will be incremented per send operation, and then just identify the subset of connections with the largest count values, and then perform on those connections the switch to RC. There are two primary issues in this naive solution. The first one is counter storage. storing it. If we store the counter for each connection, it's not scalable, as I said, because we talk about large scale scenarios. So we want somehow to store this information otherwhere. And the second issue is counter update, which means that the count operation is performed on fast pass because we want to do it per send operation, which is fast pass. But if we do it just in this naive solution, that we just impact the fast pass performance, which is bad for us. So due to those memory scalability issues and fast pass overhead, we didn't use this approach. We need another approach. So so regarding if we look at those two issues that we saw in the previous slide, the first one is how do you update this? How do we update the counter without again impacting performance? So there are several approaches, which each one has its own advantages and disadvantages. So the first thing to think about is timing, which means whether we want to count the send operation on the start or on its completion. The second thing to think about is in which layer we want to implement the solution. It can be either in the UCP layer, which is the protocol layer of UCX, or in the UCT layer, which is the transport layer. And I will explain the constant pause. So if we look at the UCT layer, the pause that we gain is sorry. I have a question here. I will read it. When using send data as metric, discard the effect of MPI get or UCP get operator. Effect of MPI. Okay, I'm not sure I understand the question. The question that I got here is regarding using send data as metric, discard the effect of MPI get or UCP get operation. Not sure why should it affect those operations. Okay, I will try to explain. Maybe it will be clear in the next slides. So for now I'll move on, and if it's still not clear, that we will talk about later. So as I was saying, using the UCT layer to implement this solution is the main advantage is that we get that we can utilize the cookie moderation feature, which is a hardware feature, which means that we can coalesce several send operation into a single counter update operation. It significantly can improve performance because we do not have to count each and every send operation separately, but we can group them together. So this is the main advantage. But the disadvantages is that except of the IB transports, the other transports that can be used do not have this kind of feature. They do not have cookie moderation. So we'll need to distinguish them, we will need to implement separate solution for them, which is not very, which is not something we would really want to do. And the second disadvantage is that the grouping size, the coalescing sizes can change between transports. For example, if I'm not mistaken, in TCP we have some other way to group completion events, but it happens on larger sizes, and then it complicates the solution because we cannot distinguish between the different sizes, and each one of them will be counted as a single count operation, and eventually will two not equal connections would be counted as equals, and it's not something that we want. So using UCP layer, on the other hand, will be simplest implementation, but we will suffer the lack of coalescing. Eventually, the approach that we have taken is an intermediate approach, which means that we do the counting in UCP layer, but we will do it on some kind of sampling mechanism, which means we have two-layer sampling. The first layer is just like modulo sampling. For example, do sample every 1,000 packets, and then we sample only one for each 1,000, which improve performance. And the other layer of sampling is just toggling in terms of time range, which means we take some few seconds, and after a few seconds of sampling, we turn off for a few seconds, and then it can also improve performance. In any case, we still need to add extra branch instruction to the fast pass in order to check whether or not we want to do this counting mechanism. And the presence of this extra branch instruction will harm performance in some way. So the way that we solved it is by combining this branch into existing branch. We fused some old existing branch which was used to, for example, check message size, yes, in order to know in which protocol to send the message. So we fused the new demand for the counter branch instruction into this threshold branch instruction, and then it solved this issue. So moving to the second issue, talked about counter storage solution. Where do we store this counter in order to do not use too much memory. So the solution here is multi-stage statistical sampling. Basically, what means we have the bottom layer, which is in LRU structure, which is the size of for example, max allowed RC connections, let's say 20. So it has a constant, it's a global structure, which do not depend on how many connections or endpoints I have on the system. It also it only contains like 20, let's say, entries. And what it does, it gives us momentarily information regarding in a specific moment in time which connections are the most active connections. But using only LRU is not enough because it does not gives us the overtime information. It does not give us the counter data because it doesn't hold counters. It only holds pointers to the EP to the connections. So we need another layer. The second layer here is some kind of aggregation array, which holds a single entry per prioritized connection. Yes, those 20 connections that he was talking about. And for each one, it calculates exponential decay score. I will explain about this formula in the next slide. So when we thought about the solution for this issue, we came up with several approaches. The first one was moving window approach, which means that using the LRU with those 20 entries, we can take a snapshot, several snapshots of this LRU, for example, in each second, yeah, for like 20 seconds or something like that, and then we can always look at the last 20 seconds and create a moving window of snapshots. So this method is very simple to implement, but it requires a lot of memory because it's a FIFO-based approach. Yeah, we need to maintain a FIFO of snapshots, and we need to calculate each time the new window that we use. So high memory consumption. And then the next approach is jumping window, which means that we do not move the window. Each snapshot, we just after 20 seconds we create it all from scratch, and then we have the last 20 seconds, but not in every second, in every 20 seconds. So in this approach, it's a hit counter based score. We count how many hits we have per each entry. It does not require FIFO, so this is why it's a bit better in terms of memory, but it's still not what we want, because it has this need to store the 20-second window, which is complexing the solution. So what we eventually selected is the exponential decay method, which only needs to hold single entry per connection, and in each sampling of the LRU, we update each entry with the new score of the exponential decay. So a bit about exponential decay. It's a formula which rewards heavily used connections by raising the score each time they are sampled. Idle connection score is lowered because they do not appear on the last snapshots of the LRU. And what it means that older connections is harder to replace because they have a lot of history. They have a lot of snapshots that they gathered, and it is calculated all on the formula of the exponent. So exponential decay. So here I simplified a bit the equation, but as you can see, something like that, which means we take the aggregated score so far, which is this one, and we multiply it by some coefficient, which is we call it decay coefficients, and then add some another coefficient, and all of this is equals to the new score. And what is worth noticing is that we decided to give more weight to this multiplier. For example, we take it as 0.8 as opposed to this coefficient, which we use 0.2 because we would like entries that is already in the structure. We want them to be harder to remove, so we give more weight to the history of the entries. Okay, so a bit about the way the usage tracker component. It's a component which tracks and prioritizes connection according to the usage, and it's a generic UCS data. It's written as a generic data structure in the UCS layer because we want it to be independent of particular transports. We wanted to make it as some infrastructure. The main advantage in using it is, of course, as I mentioned before, is avoid storing data per connection. Yes, it's a global structure. It only keeps a small number of connections. And the total memory footprint, because of this, is constant rather than O of n if we would use the naive solution. Okay, some terms that we will use in the next slide is promotion, which means the transition of a connection to a highly used connection. We do not use the terms RC and DC because this is a generic infrastructure. So promotion is just taking the connection and turning it into a highly used connection. And demotion is the opposite way around, the opposite of promotion. So basically, the usage tracker contains a connection table which corresponds to highly used connections, and on each progress operation, the LRU cache is flushed into the table to produce updated scores. Entry points for the class is usage tracker touch, which is the API for updating the LRU. Each time a new packet is sampled. And progress, usage tracker progress, which is the update operation of the connection table with new scores and adjust. And this progress is called for MU6 periodic callback context. It happens once every a period of time. And the output is notification, callback notification for motion or demotion events. Worth mentioning that asymmetric bidirectional connections can be updated according to remote side, which means if we have connections which has a lot of data moving from one side but a small amount to the other side, then remote and local nodes can exchange this data and decide according to which transport to use. This is some simplified simplified drawing of how the usage tracker works. So we have the fastpass part. All of this part should happen in constant time. So we have each message, each cookie that we get from the transmission enters the LRU. LRU uses a hash table to map it into somewhere or into the array. So hash table is the main cost is the hash function, but still it's a constant cost. So this is the fast pass, and this part is also the main connection table of the exponential decay. We can see here the most recently sampled connect endpoints. Each one has its own score, and once we produce this table, we need to filter out the most lowest endpoints out of the table, and also we need to sort it. And once we sorted it, we have our RC list ready, because we know that those few endpoints are the sampled and most highly used endpoints. And this operation is done each and every snapshot. This snapshot in t equals 0, and this is snapshot in t equals 1, and this arrow just shows that it may the list may change. So moving on to the next part, it's the transport negotiation protocol. So as I mentioned before, we need some protocol to negotiate between nodes because each node may have a different view of how much traffic amount relative to other APs he is using. So and also a single node does not have the knowledge of the RC capacity which is already in use by his neighbor, which means maybe the neighbor has already exhausted the RC resources and he doesn't know it. So we need to sync between them with a new protocol. And if we just zoom out for a second, if we had all the information theoretically about about the scores of each connection for each of one of the nodes on the network, so we could have the optimal decision about how to use the different transports across the network, but we do not have this information because we are running on the single node level. So we just try to get to a solution which is close enough to the best solution. Also, I was mentioning that a negotiation protocol must ensure consensus and avoid infinite loops, which can happen if we have some protocol which is not, let's say, deterministic. Okay. So here I just try to explain the protocol with an example. So let's say we have 4 nodes on the network, and we start from here. The usage tracker promote runs periodically, and each time it checks if there is new highly used connections, and if it does identify one of them, then it triggers promotion request to the next node, this node B. So node B gets the promotion request, and it processes the request, and it can decide whether or not to accept it. In this case, it does accept the request because it is a better connection. So it sends ACK back to node to let it know that the request was accepted. And on the other hand, it sent the motion request because we must not go above the maximum RC resources, which is 15. So we must also demote one of the nodes. So the motion request is sent to node C. And node C in turn can also, can also call the promote procedure from the usage tracker class and promote and trigger another promotion request to another node, in this case node D. Because we want always to keep the max RC connections. So if we have 14, we would like to promote another one. So in this case, this request is also accepted. So an ACK is returned. And also here we want to go back to 15, so the motion request is set. So this is basically and we also, this protocol does not allow, as I said before, does not guarantee the optimal solution, which means maybe there's some other group of connections which is better switching to RC, but it does guarantee that we will be close enough to the optimal solution. With each node has at most 15 RC connections. All the rest will be DC. Some nodes may have less than 15 because of the motion request, which in this protocol we cannot deny this request. The motion request must be accepted. So we can have less than 15 RC connections. Okay, moving to the next example. This example is pretty similar, except of one thing that I Here we have already 15 RC connections, so node D sends a NAC, which means the request was denied, which is also part of the negotiation protocol. In this case, we do not limit node C to stop sending further requests. So it will keep periodically send promotion requests and will keep to be denied, but it's okay because it doesn't happen enough times to harm performance. It's not part of the fastpass. So either if it's adding some extra overhead, it's not really a large overhead. And we just preferred to keep the protocol simple, so it will. I also was mentioning here that there's significant to the distribution of traffic across different nodes and different connections. For example, we can check Gauss distribution, or we can check unified distribution, and it may have different results for this protocol. It may have different final stage, and as part of the POC that we made for this feature, I created some script in Python which tested some kinds of distributions, so different distributions, to actually see that the protocol produces the required results. Okay, regarding switching, this is the third and last part of the feature. I will first want to just a bit explain about the wire process of the system, and then to show the modification needed in order to implement the feature. So we start from the first stage where we have multiple lanes per sender and receiver. Each lane corresponds to specific device and transport. Okay, so we start when we start the connection process, we wrap each one of the lanes in a structure which is called wire RPP, which is basically intended to block all traffic which gets to this lane and redirect it to some pending queue until the connection established successfully. So each lane is wrapped with this wire RPP, except here I gave example to a lane which does not require this handshake. For example, some transports like DC, they do not require all the wire process, all the handshake, because they have all required information, so they immediately get connected. Okay, so users start sending messages, so they all go to the pending queue, except the connected lane. And in this stage, we start exchanging information. So we send wire up request, it is called, from sender to receiver, which, for example, it may contain QP number of destination if we want to create an RC connection. So we send it to the other side, and the other side replies with its own information. and this in this stage the connection is completed. So we move the messages back to the lanes, and now we can send them. So the first stop they have, sorry. Okay, I will try to short it. So each one gets a protocol in the protocol selection process, and just fire up the receiver. Quick overview of the modification we needed in order to switch under traffic. We need to guarantee order for active message transports. We want to reuse connection which can be reused because they did not change, and pending request, as I showed in the previous slide, is handled by the new connection. Outstanding requests, which means already posted to the hardware, are flashed, and multi-fragment requests reset TCP protocols. And this is a quick demonstration. So here we start from a stage when the system already has traffic in it. So as you can see, some of the messages are already posted to hardware, some did not. And this is the receiver side message. So we start by disconnecting the lanes. Some of them may be reused. We continue by sending the messages to the pending queue. And then we reconfigure the lanes, which means we can swap between them if needed. So now what happens is the old active message message is sent through the old lane of the active message because it already was posted to the hardware, so it only needed to be flashed. After that, we send the request, and it must happen after the request send must happen after we sent all the messages on the active message lane in order to guarantee the order of messages. Same thing on the other side, and then we are fully connected and can retransmit as we done before. Okay, so regarding benchmarks, we used two basic ones, OSU-MBWMR, which has few highly active endpoints and a lot of unused EPs. It was mainly used to verify switching of correct EPs. And we used also OSU all-to-all, which is a symmetric scenario where all EPs send a lot of data to each other. And this was used to check avoidance of excessive switching, as I mentioned. And also we took the OSU-MBWMR and improved it a bit. We added some extra send operation on all the unused EPs in order to better simulate real use cases. That's it. Questions?
When do we expect this in upstream?
During this 24.
Sometime 24. All right.
All right, let's thank the speaker.
Thank you.
That was our last talk for today, so we're going to adjourn until tomorrow.
Okay, thank you. Thank you for all the online attendees and for presenting today. For all the guys in Europe and Israel, thank you for staying late again. And we'll meet tomorrow again. Hopefully, we'll make it on time.
All right, thanks everybody.